Today we'll be starting our second last Year 11 topic, which is on probability. Now, a lot of this you would have seen last year already in Year 10. Some of the notation, when it comes to the set notation, you may have looked at in Year 10 as well, but some of it might be new to you as well. So just to start off with, we're looking at a fair bit of review from your junior school. So we're looking at probability and sample spaces. So the first thing we're going to look at is what it means for outcomes to be equally likely. So these are the words. If we have outcomes that are equally likely, it means that firstly, exactly one of those outcomes will occur, and any outcome is not more likely to occur than another. So firstly, definitely something has to happen. So one of those outcomes must be the result. And the second thing is that each of the outcomes have the exact same chance to happen. So if we have an experiment of n number of equally likely outcomes, then the probability of each of those individual items is 1 out of n. Okay, so if I'm looking at rolling a die, I've got 6 sides on a die, so then the probability of getting any of those sides is 1 out of 6 in an equally likely situation. When we go about calculating probability, so the notation that we use P bracket, and then inside we write down what the event is. So whatever we want to find the value of. So if we're tossing a coin and we want heads, then it'll be P bracket heads. To work out the probability, it's the number of favorable outcomes over the total number of outcomes. So how many ways do we have of getting what we want over how many different possibilities were available to us? This total number of outcomes is also sometimes called the sample space or the event space. So the sample space is the set of all your possible outcomes, and in a uniform sample space, each of those outcomes is equally likely. When we're looking at the event space, we're looking at just those favorable outcomes. Often we'll use a Venn diagram to show this information, and it is quite useful because then it gives you an image to work to base your probability off. So if I were to throw a standard die, okay, so just normal die, the sample space is going to be S, okay, so S for set, and we use curly brackets. So inside we just list out what the possible outcomes were. So for a standard die, it would be 1, 2, 3, 4, 5, or 6. If we want an event rolling a number greater than 3, then the event space, okay, as we said here, the favorable outcomes, the event space is any number greater than 3, which is 4, 5, and 6. So what we've got here is, if I were to draw a Venn diagram, very simple one, there's my environment, so everything's going to be contained in here, your sample space, and then you've got the event in the middle here. So if I want the event is rolling a number greater than 3, then we've got a 4, 5, or 6 inside of the event space, and then anything else remaining will be outside in the environment here. So if I've got 4, 5, and 6 on the inside, then 1, 2, and 3 are going to be on the outside. So that's a way that we can write it out. So if I wanted to work out the probability of getting the event, then that would be 3 items out of the total of 6 items. Other words that we do see a fair bit of is impossible and certain. If an event is impossible, then the probability is equal to 0. Okay, so that means it's never going to happen. So it's like if I have a bag full of red marbles and blue marbles and I want to pick a green marble. Well, it's never going to happen. So then the probability is equal to 0. If an event is certain to happen, so it's 100% like definitely going to happen, then the sample space is exactly the same as the event space, which means that the probability is going to be 1, okay, 1 or 100%. For anything else, it's going to be a number between 0 and 1. So you can't have numbers greater than 1 and you can't have negative numbers either. Okay, so anything else is between 0 and 1. I've used just the less than symbols without the including, okay, because I'm talking about anything else except for the impossible and certain events. Still got a couple more bits of terminology that we'll work through. The next thing is a complementary event. So complementary, the word complementary means that it matches together. So when we talk about complementary angles, we talk about two angles that match together. Complementary events are two events that add together, that match together. And basically, if you add them together, it's equal to 1. So the idea of a complementary event is we're looking for the probability that the event does not occur. So it's really the opposite. Often you'll see the word not used a lot when we're talking about complements as well. So if I want the complement of E, then it's all the outcomes where E does not occur. Now, there's different ways that we can write this out. We can write it with E with a line on top. Sometimes we'll use a little dash. So dashes are used in a lot of places. We use them in differentiation, and we're using them now in probability as well. So it's important that you look at the context of your question. Another way that we write it is with a little c. And again, another notation that's being repeated. Remember, we looked at using a little c for radians. Again, you need to look at the context of your question. So basically, if I want the sample space, it's going to be everything in the event and everything not in the event added together. So that means the probability of adding together the event with what it's not should equal to 1. So a way that we can calculate complementary events is to do 1 minus whatever the original event was. Okay, or if you wanted to find an event, you're doing 1 minus whatever the complement is. Often we use complementary events a lot when we see the word not. Okay, so if it's not, then it's a lot easier to work out when it is, and then you can subtract it from 1. At least is also another word, and at most. So if I want at least one item, then the opposite of that is getting no items. And it's a lot easier to work that out often than trying to work out all the different possible values for having at least, like having the minimum of one item. The last little bit of terminology we're going to look at is invalid arguments. So sometimes we'll have a probability statement where it actually doesn't make sense, or the probability doesn't actually work. So sometimes these are usually called fallacies. Okay, so a fallacy in the argument means that there's an issue with the intention of the question or the interpretation of the question. So here's an example. There are 14 students in our class, so the probability a particular student comes first is 1 out of 14. Now, if we look at it exactly as it is, basically I'm saying there's 14 people and I'm just going to pick a person at random and they're going to come first. Now, obviously, that's not really going to happen. So there are 14 distinct outcomes, but they're not all equally likely because there might be a student who's a little bit more hardworking than another student, or one student who understands the concept a lot better than some of the other students. So each of these outcomes, even though there's 14 separate ones, they're not all equally likely. So how you would go about solving these, like explaining these sorts of questions, you'd say, look, we do have 14 outcomes. Each one is not equally likely. And then we want to offer a way in which this statement could be true. So with a little bit more information, this statement could be true. So I've said, however, if an external person was to randomly choose a student in the class, then that person has a 1 in 14 chance of choosing the person who came first. So if someone comes in, has no idea about the class and just goes, I think you came first, then they've got a 1 in 14 chance of picking that. And it's because it's a random choice. So with these sorts of questions, what you want to do is explain what the problem is, and then if you can, offer an alternative. Okay, these sorts of explain questions can appear. They can be worth 2 or 3 marks each. So part of it is saying which one and then what your justification is. for the most part, if you just said, so if you had a choice of two and you just said A or B, then you won't really get any marks, even if you picked the right person. Okay, so it all comes down to your justification. If you don't offer justification, then you actually won't get any marks. All right, couple more things. We talk about relative frequency or experimental probability. So if you remember back to junior school, you talked about theoretical probability and experimental probability. Theoretical probability is what we know, or it's a calculated probability, what we know should be happening. In experimental probability, often we may not know exactly what the probability is because of the nature of the experiment, or you might be testing out a theoretical probability by actually performing an experiment. So, okay, so experimental experiments. So in these situations, basically you're still doing the same thing. You're looking at how many of your results are favorable over the total number of experiments that you conducted. Now, just before we finish off, a couple of sample spaces that you will see a fair bit of, and you do need to know how much is each of these. So if I'm looking at dice, okay, so one is a die and more than one is a dice. Most typical dice have 6 sides, and you've got the numbers 1 to 6. Obviously, they can change it up, and they'll give you more information if they want you to use a non-standard die. So 6 sides on a die. It's also important, you know, about the letters of our alphabet. So we've got 26 letters altogether in the alphabet. There's 21 consonants and 5 vowels. So your vowels are A, E, I, O, and U. Okay, so just make sure you remember that. So consonants and vowels. The last one, very important, and if you don't know this, you really do need to, you know, get out a pack of playing cards or find a way to learn these. When we're looking at a deck of playing cards, we've got 52 cards altogether. We've got 2 colors. We can have red or black. We have 4 suits, and that's spades, hearts, clubs, and diamonds. We've got picture cards. So picture cards are your Jack, Queen, and King. Jack, Queen, and King, or King, Queen, and Jack. Ace is usually counted as 1, so you can just leave that one off. And then you've got your number card. So you've got your ace, okay, which is usually 1, and then you've got the numbers 2 to 10. So you've got, for each suit, you've got 10 number cards and 3 picture cards, which means each of your suits have a total of 13 cards. If you don't know those, make sure you do go have a look at a deck of playing cards. I know most of your textbooks will have a picture of all the different types of playing cards. Make sure you familiarize yourself with that. All right, have a go at some of these questions. Most of this is your simple probability. You shouldn't have too many issues with it. If you do, let me know and we can work through these together.